And now, please welcome Dr. Dev Palmer.
So, what does the word environment mean to the DoD? For the purpose of assessing the reliability and functionality of electronics, MIL Standard 883 defines the environment as the natural elements and conditions surrounding military and space operations that could have deleterious effects on electronic systems. To be certain, the warfighter's operating environments are more extreme than what most of us would encounter, say, on a drive to the office, or even on a drive around the world. Today's military conducts missions on the ground, on and under the sea surface, in the air, and with the addition of the U.S. Space Force, to the edges of cislunar space. And the electronic systems needed to accomplish these missions must operate without fail in cold weather, in hot weather, in an electrical storm, in the air, on or under the sea, in space, in a tank, jet, helicopter, submarine, aircraft carrier, on a satellite, or inside a missile. But so far, we're talking about electronic systems that can tolerate extreme environments. What about electronics that are designed to thrive in extreme environments? So good afternoon, I'm Dev Palmer, Deputy Director of the Microsystems Technology Office, and I'd like to welcome you to the Extreme Environmental Electronics Technology Discussion Panel. Future MTO research on electronics for extreme environments will focus on three elements and conditions in particular: high radiation, extreme temperature, and high power, which is high voltage and high current. Each of these elements and conditions present their own unique challenges and opportunities. Radiation damage can be caused by energetic particles in high-intensity electromagnetic fields, resulting in effects ranging from resets and failures from glitchy signal spikes and noise to physical damage and system shutdown. Environments with high levels of radiation can be natural: lightning strikes, the Van Allen radiation belts, geomagnetic storms like the mild one that's predicted to hit today, or produced by human activity, high-energy physics labs, nuclear reactors, and the intense electromagnetic pulse from a nuclear explosion. Generally speaking, electronics in these environments have to have the same functionality as any other electronics. So we need to find solutions to improve radiation tolerance in digital and mixed signal electronics, including ASICs and FPGAs, and also in complex heterogeneous microsystems. As far as extreme temperature goes, normal military electronics are expected to operate reliably from minus 55 to 150 degrees C, or roughly minus 70 to 300 degrees Fahrenheit. How does that compare to natural temperature extremes? The lowest known natural temperature on Earth, minus 128 Fahrenheit, was recorded in 1983 at the Soviet Vostok station in Antarctica. The highest known natural temperature recorded on Earth, 135 degrees Fahrenheit, was measured in 1913 in Death Valley, California in the US. But oil and gas wells can reach temperatures exceeding 400 degrees Fahrenheit, and emerging research on hypersonic vehicles shows that the nose cone and wings heat up to over 3,000 degrees Fahrenheit at Mach 5, and the inside of the jet engine can get much hotter than that. We won't be able to get the best performance out of these systems if we can't build the sensors, communications, and control circuitry for them. But not all extreme environments occur outside of the electronics. Operation at high power can stress the microelectronics and everything around it. The bottom line in that domain is that we need to develop new devices that can control high voltage, high current, and high power, along with high breakdown insulating materials and low loss passive components, and the design software that enables us to reduce the research to practice. So now I'd like to introduce our panelists. Please scan the QR code in the Slido app to submit your questions. First, L.J. Petersen is a program officer at the Office of Naval Research. He earned a BS in mathematics from the U.S. Naval Academy in Annapolis, Maryland in 1986 and commissioned as an ensign. As an engineering duty officer, he earned the master's in mechanical engineering from the Naval Postgraduate School in Monterey, California. Following active duty, he was an electrical engineer at the Naval Surface Warfare Center, Carteret Division, Annapolis Detachment, followed by a tour as the ONR Science and Technology Representative to the Electric Ships Office, or PMS 320. He was recalled to active duty in 2008 and served as the Deputy Director for PMS 320. Later, he was the Navy's Director of Systems Engineering, assigned in the Deputy Assistant Secretary of the Navy for Research, Development, Test, and Evaluation. LJ retired from the Navy in 2016 following 30 years of service, and now leads basic research in power electronics and related technical areas at ONR. Todd Bauer is a distinguished member of the technical staff in the Microsystems Engineering and Applications Complex at Sandia National Laboratories. At Mesa, Todd is a process and integration engineer who's led and supported teams that have delivered radiation-hardened microelectronics, sensors, MEMS, and trust and assurance technologies to national security partners. Todd has over 25 journal and conference papers and holds 16 patents. He also has 2 R&D 100 awards for energy harvesting micro power sources and for integrated circuit authentication technology. Prior to joining Sandia in 2001, he earned his PhD in chemical and nuclear engineering from the University of New Mexico. Rusty Gilbert is the owner of J.R. Gilbert Energy, LLC, where he advises energy businesses on investment options, development, and commercialization of innovative technology solutions. He served more than 40 years with Chevron and Gulf Oil, ultimately as General Manager of New Technology Development and Adoption for Chevron Technology Ventures. He's developed technology to reduce cost and increase performance at sites around the world, and has held numerous leadership assignments in R&D, which supported Chevron's worldwide shale plays, as well as provided stratigraphic and reservoir modeling support for worldwide major capital projects. Other leadership assignments include exploration, production, and new ventures campaigns in the US, Africa, and Asia. He earned the BS and MS degrees in geology from Rutgers University and the University of Massachusetts at Amherst. So we're going to start out with some statements from each of the panelists. LJ, can you tell me what you see as some issues and opportunities in the power electronics domain?
Yes, thank you, Deb. Well, first of all, I am from the Office of Naval Research, and very briefly, ONR is made up with 5 departments. We were formed after World War II, signed into law by President Truman to give our warfighters, in particular our Marines and our sailors, an unfair technological advantage over their adversaries. In power and energy at ONR, we are really pushing the extreme environment, if you will, of high switching frequency, high voltage, high current. We have developed silicon carbide along with DARPA in cooperative efforts and the other services to get where we're at today with a medium voltage MOSFET technologies, as well as other switching device technologies. Some of the challenges, though, that we're facing as we go forward, as others are developing ultra-wide bandgap and extreme wide bandgap semiconductors. The semiconductors themselves are not going to be ultimately the challenge, but it's the magnetic materials, it's the controls, it's the way to handle thermal management, because as things shrink or get significantly smaller, that poses huge thermal management challenges, because surface area is the friend of the thermal management engineer. So ways to overcome that. And then also modeling challenges, which I'll get into a little bit later, pose opportunities. We are headed down a revolutionary path called PPEDS, Power Electronic Power Distribution System. And that is cutting edge. It's basically a network of PEBs, or power electronic building block converters, that communicate, and we're going to distribute energy in packets very similar to the communication industry had done about 10 years ago. And so I have a program review on Thursday and Friday. If anyone is interested, I'll be glad to give you a link, and you can see a little bit more and learn a little bit more about the challenges and risks that we're trying to overcome in power electronic power distribution systems. Thank you, Dev.
Thank you. Todd, what about radiation-hardened electronics?
Yeah, thanks. And I just want to say that LJ reminded me backstage that he funds some of the work that we do at Sandia, so I'm going to be on my best behavior, sit next to him today.
Thank you.
So challenges and opportunities in radiation-hardened microelectronics. It's on the challenges side, it's a very esoteric body of work, right? It's an esoteric practice to harden microelectronics that are typically available commercially, right? We in the national security community are often left to our own devices to figure out how to do that using our own facilities because there's no market for it in the commercial world. That's an enduring challenge that we continue to struggle with today. But on the opportunity side, what we're finding is that things like collection volumes for particle strikes and integrated circuit are getting smaller and smaller. And so commercial microelectronics are actually getting a little bit harder, which is working in our favor. Looking forward to exploring that more, exploiting that in the future. Is there going to be an intersection between commercial microelectronics and national security microelectronics for radiation environments? The third point that I want to bring up is it straddles the fence between opportunity and challenge, and that's heterogeneously integrated microelectronics, right? So you have this disaggregated system where you can potentially take the best in breed of each function that you want to incorporate into your system, but what those interfaces look like, how you manage those interfaces, ensuring that one interface is not fatally sensitive to radiation environments, I think is going to be a really big challenge, something that we're tackling at the laboratories. Looking forward to hearing your thoughts on that. Deb, thank you.
Thank you. Rusty?
Yeah, thanks. And again, appreciate being here and glad you're all present. I know there's a lot of people online. With the challenges, right, I think my part of the panel is kind of representing the energy side, maybe more oil and gas, but I can represent renewables to some extent, right? We're dealing with a lot of sensing technologies, right? We've got sensors on the surface, measuring production and flow. We've got sensors while we're drilling the wells because we need to know when we're drilling the wells what the performance is, what formations we're in, how fast we're going, because we need to target certain formations deep in the earth, and the oil and gas usually isn't found everywhere, which some people think you just maybe drill a well and you find oil and gas. A lot of times you have to drill in very specific locations in order to get the best reservoir and performance. And the technology is gradually catching up, but there's still room to grow relative to where we need to be, especially with the deeper reservoirs that are hotter and higher pressure. Dev mentioned it kind of in the beginning. There's a lot of vibration issues with all the tools while the well's being drilled. There's a lot of corrosion issues, not only when you're drilling the well, but when you're producing the fluids. And there's distances involved. Some of these locations, if you're offshore, you could be hundreds of miles, literally, from kind of a home base, and you need to transfer the data, and you got to make decisions around what do you do that analytics kind of locally, or do you transmit all the data and do it kind of at the home base or some kind of hybrid model? So what I see is there's a lot of overlap between what we're trying to solve and resolve in the energy business and what some of the other verticals are doing. In this case, the defense industry. You're faced with, in some cases, some of the same problems. Now, granted, our temperatures aren't as hot as maybe a ballistic missile or something, but for a lot of the other weaponry, we're kind of dealing with some of the same extreme temperatures and pressures, and it needs to be reliable, right? If it's not reliable, I'm just guessing, right? On the military side, we're looking at perhaps casualties or worse, and in the oil field, you're looking at a lot of downtime and performance issues, and you may never get to the reservoir objective. So even though the challenges are slightly different, there's also some similarities between the two. So I'll leave it there. Thanks.
Thank you. So we're going to go right into the Q&A, and the first one up here is probably best answered by Todd. What are some of the major bottlenecks for test and evaluation of rad-hard electronics?
Yeah, it's a big problem these days. These are massive infrastructure builds, right? Think accelerators, beam lines at national laboratories, that sort of thing. And what we're finding is that increasingly the commercial world is interested in radiation testing their microelectronics. Think about a world enabled by autonomous systems, right? You can't tolerate a single event upset in that system. You can't have a functional interrupt, for instance. And so commercial companies are interested in testing their hardware, so we're competing with them. We've always been competing, and I want to put some air quotes around that. It's not an ugly competition, but we've been competing with people that do pure research, university groups, and that sort of thing. Folks that are doing basic science. And so, for national security applications, oftentimes we're doing things like running our tests at midnight because that's when the beam time is available, and that's hard work. That takes a certain level of dedication. The competition is stiff enough for facility time that we're literally planning 6 months out, a year out, to get that facility time. Now, that's a challenge. On the opportunity side, there are some cool programs. Dave Abe at DARPA is looking at, is considering emulation. Can you emulate a microelectronics system and do something like fault injection for maybe a security glitch, for instance, and use that as proxy for how microelectronics are going to behave in radiation environments? So that's an interesting thing on the opportunity side. We'll see where the science goes on that, but it's we're following it closely because it potentially alleviates a pain point for us, which is just getting the test time that we need to evaluate our systems.
Are there similar challenges in the other domains? LJ? Test and evaluation of power.
Yeah, for our domains that we're looking at is we don't have a lot of high voltage or high power test facilities as we're trying to go up, as we're trying to increase. Zumwalt, for example, has 78 megawatts of installed power, and we did have a test facility at NSWC Philadelphia. But as we go forward and look at different architectures, for example, medium voltage DC or maybe even medium frequency AC, coming up with the facilities, the people, the trained and skilled people that to operate the facilities and to characterize and capture, those are our challenges as well.
And just in case folks in the audience aren't familiar, Zumwalt's a new destroyer, is that right?
Yes, the Navy has built 3 of them, the Zumwalt class, DDG 1000, and similar to the Seawolf class, where there were only 3, we're learning a lot from that technology, as that was the first Navy's electric drive platform, and DDG-X is the follow-on now under the direction of the PMS 460 program office.
Great. Got another question coming in. Rusty, do you see any new trends in device topologies, new materials, and new strategies for integration and packaging to withstand extreme temperatures?
Yeah, thanks for that question, wherever it came from. And I'll roll a little bit maybe of what my response would have been from the last question into the answer for this question. I represent, and I'm canvassing all the time, kind of new startup companies in energy field, and there's literally hundreds of them, and we're seeing new innovation all the time. And part of the problem is they're not well funded, and even though some of the technology is really good, right, we're trying to enable them with field trials and funding. But some of the changes that we see, I'll maybe pick 2 examples, and maybe they're not perfect examples, but it gives you kind of a flavor of what's going on. The fiber optic technology is really a blossoming field right now, and I think there is overlap, right, between the energy field and some of the other verticals, including maybe military use. We first deployed that. My group actually first deployed that in Chevron, and we were a little bit late to the game. It was probably 10 years ago. It was a bit of a test case for us, and it was successful. And we were actually able to measure acoustics and temperature in the subsurface in real time at least a foot intervals over a lateral that went about 6,000 feet down and about 5,000 feet out. Fairly long well. There are longer wells. And we were able to monitor it in kind of real time to understand what's going on. Now, the benefit of that was we were able to frack the well in a certain way to be able to maximize the fracture lengths, to be able to recover the most. In this case, it was natural gas because we weren't in an oil zone. And that technology use within the company that I had worked for, right, blossomed to be able to image the subsurface, to be able to see like a clear X-ray picture of what the subsurface looked like, very far deep into the earth by deploying the same type of technology. And we were able to drill wells a lot better, a lot accurately, and just do things better at lower cost. The other example I'll mention, and I'm not as well versed here, and I know we have a few material science people in the audience because at least one raised their hand before. There's new materials coming out occasionally, and graphene is one. And with graphene, it's extremely light, it's extremely hard and durable, could be as strong as steel. It can be mixed with other materials like rubber to be able to strengthen tires, presumably in military use, or car truck tires. So there's challenges ahead with how do you mix, the graphene in the existing material to get a distribution so that it does what you want it to. But those are two examples where we can maybe get around and look at the problem and solution a different way and come up with some innovation so we bypass maybe the impediments that we would normally have with just, say, temperature pressure with electronics. Is that okay?
Rusty, how long do your systems need to last? And are they disposable?
Good.
Or
Yeah, that's perfect. Yeah, thanks a lot. So we had, like fiber optics, I'll go back to the first example. There's a permanent solution and there's a temporary solution. And of course, there are different companies that do each, but there's business cases for both cases, right? In some cases, you want to monitor the well for the whole length of the well to see how it changes, because it's like your body. You go to hopefully to the doctor once a year and you get a physical and all kind of measurements. Well, with the subsurface, you're able to do that with this permanent fiber. There's benefits of having it just temporary, because some of the key problem solutions that you need are just in the beginning, and you can drop a very cheap, like 1,000 times cheaper than the permanent one, into the hole and get excellent data for at least 2 weeks. And that gives you a snapshot of what the health of the production is, and you don't really need any more, or if you do, you just do it again. So those are two solutions where sometimes you don't need the foolproof permanent solution. If you design it for a temporary solution, it could be better.
So we have one other question come in here, and this looks like Todd's going to field it first. How is PLEO and radiation tolerance going to impact or change the radiation-hardened approach to components?
Yeah, it's interesting. So when you think about computing on satellites, oftentimes you're thinking about computing on the edge, and you need some true compute power, right? So you're thinking about commercial capabilities, but those aren't necessarily always as hard as we want them to be. And so we're exploring concepts like radiation hardened by design to help get us where we need to be within commercial infrastructure. Even that though has some limits. I'm not answering the question. I guess I'm sort of stating the obvious here. What the future looks like. I'm excited that there may be an intersection between commercial microelectronics and radiation-hardened microelectronics. That'll go a long way towards addressing some of these compute at the edge problems that today don't have really elegant solutions, right? We sort of take some of the warts that come with operating commercial electronics in radiation environments, accept shorter lifetimes, but there's possibly a future where the compute that we want at the edge is going to be a little more durable, a little bit higher reliability in extreme environments.
Yes, certainly the number of PLEO satellites is probably going to be at least as large as the number of components that the radiation-hard components of DoD buys.
We're excited to see if that becomes a true commercial driver, right? Yep. Drive some investment in this area.
So, LJ, here's another question. Okay. Other than the semiconductor devices themselves, what are some of the critical research areas in power electronics?
Okay. Thank you, Dev. And so, as was mentioned earlier, it was a question on reliability and how long things must last. And so we're trying to maximize reliability. In fact, we're trying to maximize all of our LED's availability because we know the operator, the warfighter, the Marine and the sailor that's going to operate it. So thermal management is one area. My colleague, Dr. Mark Spector at the Office of Naval Research, he and I are managing in the 4th year of a 5-year MURI. That's a multiple university research initiative that's being led right here by Georgia Tech, Dr. Sam Graham and Alan Doolittle. And just this past year, under this thermal barrier resistance focus, Dr. Doolittle, and no pun intended, that is his name. He's here in the electrical and computer engineering department. Great scientist. His team discovered P-type doping of aluminum nitride. And so I asked him, I said, so what's the next step to realize this as a MOSFET module, and he says, well, we need low-loss ohmic contacts, and so we're looking at ohmic contacts as part of that package as well. Packaging, we do not have in industry today a standard for packaging, and we're seeing this in some of our programs through degradation in partial discharge inception voltage. The more we operate, the lower the PDIV or corona inception starts to drop. So that also leads to better insulation materials, as Dev had mentioned in the opening. So those are definite areas, and also to be able to realize semiconductors, as I mentioned in my opening, in very compact, high swap, size, weight, and power, reduced cost applications for a warfighter. We need soft magnetic materials. As Todd mentioned, I am funding some research at Sandia, also the University of Pittsburgh, and at Northeastern University, looking at soft magnetic materials, magnetic amorphous nanocrystalline materials, for example, to be able to be used as passive components, soft magnetic materials for inductors. And then in the Navy, we have a requirement for galvanic isolation and for our solid-state transformers. So those are areas, in addition to the semiconductors themselves, that are going to be able to realize the PPED system that I mentioned in the opening.
We've got another good question in here that is applicable to everybody. So let's start with you, Rusty. What's the single most difficult environmental case you're most worried about now?
Yeah, I mean, it's a great question. I could answer it maybe at least 3 different ways, whether it's tied specifically to electronics or not. But you know, if I deviate a little bit from that, but it's a little bit related too, right? I mean, we're just getting inundated with everything's got to be EVs, right? Everything's being electrified. I think there's still a huge case to preserve hydrocarbons, and we, heard from the prior speaker or speakers. The layered model is best in the military. Well, it's also best in the energy field. You need different sources of energy. Where I'm going with this is in the EV area, and you really need a lot of critical materials and metals that aren't readily available in the United States. Lithium being probably the most prominent one, but there's molybdenum, manganese, magnesium, and a few others that you have to surface mine. And that, in general, we've shut down surface mines in the United States. There's a few still left, but generally the lithium comes from surface deposits. Now, you can drill wells for lithium, and that's being done right now in Arkansas. But, there's a huge environmental case around how are you going to retrieve all these valuable metals and materials to make all these electronics when you're going to have to really degrade the earth, the surface, and where are you going to get the permits and speed up the regulations to that? And if we defer to the other countries, hate to say it, but most of you know it, the Chinese have tied up many of those deposits already. They don't care about the earth. They don't care about the environment, and they're polluting the air and the water. And we're buying, the cars that are already put together. So there's really some unfairness here in the whole value chain of the EV network, if that makes sense.
Rusty, I think those are important considerations, of course, and actually we have some DARPA programs that are addressing the sourcing of rare earth elements, but I think the question, actually, I should have done a little editing on the fly.
Yeah.
What's the most extreme environmental case? Like what's the most difficult environment to operate in the energy business?
Well, right now we're faced with the CO2 emissions. So we're trying to recover as much CO2 as we can because we're being mandated, right, to do that. And that's the single most issue on the energy side is reducing the emissions, which we've always been trying to do, but we're trying to do it better, the methane emissions. And then with the CO2 being produced, what do you do with all the CO2? Because generally, it doesn't convert easily into products. So you have to sequester it or do something with it.
In terms of like temperature and pressure that you've seen in some of the installations that you've installed technology in, what was the technology having to live through there in terms of high temperature and high pressure?
Right. Well, we're trying to produce reserves, deep in deeper reservoirs offshore in the Gulf of Mexico under high pressure temperature conditions, and we don't have the sensors or the logging tools to be able to evaluate the well to know what we're in or whether there's hydrocarbons there. And if those tools fail, those rig costs are millions of dollars per day, and those tools are very rare. So we need tools that can actually measure what we need to measure under these extreme temperatures and pressure conditions.
Okay, before we go to the next question, I just want to give Todd and LJ a chance to weigh in on what's the harshest environment that you see electronics facing these days.
It's an intriguing question, and they asked for what's the single most extreme environment. I want to give 3 answers, right? But I'll try to stick to one. So at Sandia National Laboratories, we're responsible for the non-nuclear components of nuclear weapons, and so the microelectronics that we deploy have to survive the most extreme nuclear blast environments, right? So high total dose rates and extreme neutron environments, which can induce both displacement damage in the channel and then also single event effects. Those are prudently applications that the commercial world just doesn't care about, and so that's something that we're responsible for, a responsibility that we care about deeply.
And in terms of the new electric boats and ships that the Navy's building, what voltage and power ranges do you think are forthcoming in those new platforms?
So for example, on Zumwalt, we have a 4160 volt system, but we're looking at 13.8 kV AC for the DDGX program office. Our carriers are comparable to that voltage. But the good thing about that with Ohm's law, as the voltage goes up for a fixed power level, that drives the current down, so you get a little bit of a benefit from that in having lower amperage rated cables to support that power that is being delivered in the ship.
Okay, great. I got another one for Todd coming in here. Traditional approaches to radiation hardening have fallen into 3 categories. Radiation hardness by architecture, design, and process. Are there new approaches either within or in addition to these?
Yeah, that's a fairly complete list. You might add shielding onto that, right? There are some environments that we can reasonably shield. If you're going to put something in orbit, of course, shielding gets really, really expensive, and it's not a practical option. But I do still think that architecture, design, and process are sort of the key ways to get there. Process is probably the most complicated. One of the challenges is that here in the U.S. we put limitations on our commercial suppliers base, where if they develop integrated circuits that are hardened beyond a certain level, it becomes ITAR controlled material, and so the commercial world is essentially disincentivized from making microelectronics with that kind of radiation response, and of course that means if you don't have your own captive facility to do that kind of work, it becomes really, really challenging. Architecture and design, those are typically the areas where we can work within commercial infrastructure, right? We can play some cool architectural tricks, some cool design tricks, body biasing of the wells, that sort of thing to mitigate the effects of radiation. Our experience though tells us that there's only so far you can get with those. It doesn't get us all the way to the goal line in terms of hardening for the most extreme environments.
Okay, so here's another interesting question. Do you see any need for cryogenic devices in circuits below 4 degrees Kelvin? For example, superconducting or topological devices. I'm not sure that lies directly within anybody's area of expertise up here. I can make a couple of comments on that if you'd like. So at least to the best of my knowledge, the drive for circuits and devices that are operating at that 4 Kelvin range is mostly in the quantum computing and quantum sensing domain. And there you have to have electronics that to pull the signals out from the quantum computers and convert the quantum calculations back into the electrical domain. What's interesting is that there have been some experiments on taking commercial CMOS circuits and operating them in liquid nitrogen temperatures, 77 Kelvin. Haven't seen any results on CMOS operated at 4 Kelvin. The interesting thing is that the performance gains are not really as much as you would hope. Really, if you're going to optimize computational circuitry to work at those temperatures, you kind of need to start from scratch. And that's part of the reason that MTO started the LT program, which is taking that first step and seeing how much we can improve the performance of standard CMOS at that 77K temperature. Anything else anybody wants to add there?
Yeah, Dev, I'll take a stab at that. As far as 4 degrees Kelvin, the answer is no. But within the last 20 years, the Navy has built 2 motors, 2 second generation YBCO, yttrium barium cuprous oxide, superconducting based motors by American Superconductor and Electric Machines. One was at 5 megawatts, the other one was at 36.5 megawatts. And they were tested. They operated under gaseous helium at about 35 degrees Kelvin with a Gifford-McMahon cryo-cooling system. But as far as anything below 4 Kelvin, I'd say no. Years ago, probably 40 years ago, the Navy at the NSWC facility in Annapolis built a DC superconducting motor, first generation superconductor that was down around 4 degrees Kelvin, nickel titanium, I believe was the superconductor for that. But nothing new, and I don't foresee anything in the future needing to operate at those temperatures.
Anything in the energy?
I can't add anything that would be worthwhile to the audience. Nothing in the energy industry, per se.
Oh, this is a great question for all the panelists as well. What is a seemingly impossible problem in this space, which if you solved it, would have a huge impact? And this is focused on instrumentation and electronics in particular. Who wants to kick that one off? Okay. I'm going to volunteer one of you in a second. Okay, LJ, since you're sitting next to me.
I think where we're going with this PPEDS, this power electronic power distribution system, that has an opportunity to really revolutionize the way that we're going. Taking energy packets, if you will, very similar to the communication network of several years ago, and then distributing them throughout this cluster of PEBs, power electronic building blocks, in a network where no load or no source is directly connected to the bus, but they're connected to each other. It's going to require active filtering along multiple converters. EMI, there's not going to be able to operate in an EMI environment. We're going to have to be able to knock that down. And then it's going to have very low latency. The communication path has to be very quick. We're doing some work right now at testing Dr. Herb Ginn at the University of South Carolina under this discretized energy control, and we're seeing latencies on the order of about 50 nanoseconds. But we really need to minimize that and then overcome the active filtering amongst multiple power converters, and that would be a significantly huge impact towards where we're trying to go with PPEDS.
So what do you see? What do you see making that seemingly impossible right now? Are there any innovations that we need to come up with? Is this mostly engineering of technologies we already have access to?
No, modeling and simulation. So right now, with computer models, there's 2 supporting objectives with models. One is we want computationally efficient models, but we also want accurate models. And having those simultaneously are competing objectives. Typically, we can get very accurate, but it takes very long periods of time to converge. But we don't have the time for it to converge. We want them to converge very quickly, but we also want them to be very accurately, and so that they're sort of. And then those 2 supporting objectives lead to ultimately where we want to go, which is the model is the spec. The model is the specification, but there's a lot that has to be done between now and then in order to bridge the behavioral models, which do very well in a time domain, with the physics-based models, which are finite element model based. And so there's a gap between the 2.
Todd?
Yeah, it's a hard question. Especially for somebody who makes microelectronics for nuclear weapons. It's an esoteric space, and we in the defense community, Department of Defense and Department of Energy dedicate huge resources to trying to work within the confines, the constraints of the commercial world to harden to levels that we need. If we could, if we just had ways to do that, that didn't rely on these exotic, esoteric, design approaches, processing approaches, it'd be pretty cool. It wouldn't be earth-shattering, but certainly it would solve a class of national security problems that we've wrestled with mightily for the last 20 or so years.
I'll take a stab at it, and I'll answer the question a little differently. If you at least connect electronics with electricity, right, something pretty basic, I'll just give a short answer because we're starting to run out of time and there might be time for yet another question. We're working on a project right now with converting ocean wave energy to electricity. And we've got a new design prototype. There's a lot of big dollars thrown in this space. We have very little dollars. People have said it's an impossible task that we're trying to do. But we're fairly determined that we have a different prototype that can be cost efficient, reliable, and placed near shore, unlike all these big multi-million dollar, hundreds of millions of dollar projects at large scale. We're thinking instead of going big, go small and be very efficient, and that's what we're working on. It's one of our challenge projects. Thanks.
So we've got another question here that I think applies generally again. What are your thoughts on the packaging, housing, interconnections, and other such ancillary materials that should not fail in extreme situations? So that's obviously asking the question, what besides the electronics needs work these days?
I'll take a stab at that, Bev. There's risks associated with in packaging. I mentioned earlier about insulation and breakdown and being able to effectively manage thermal. Under a depth score project with University of Arkansas, David Heitink and Alan Mantooth are looking at combinatorial risk reduction. And this is looking at stress and EMI impacts on solder joints and on wires that facilitate the switches. A lot of times people will try to reduce risk, one risk at a time, but many times there's combinations of these risks and simultaneously with the EMI and magnetic field on these joints, as well as the fatigue of the solders that operates in switching the devices. And so these are areas in packaging and interconnections that really need to be addressed, not only at extreme temperatures, but I submit even at room temperatures that need to be addressed.
Yes, at high power, switching on and off can create some pretty serious physical transients as well as electrical.
Correct.
Rusty?
Yeah, I'll just give a little bit of a short answer on this. And I'm just thinking of the transportation part. So we had a lot of failure of equipment going to Kazakhstan, extreme temperatures, right? Extremely cold in the winter and really hot in the summer. And by the time this material was used, maybe a year later, it was failing, and a lot of it was electronic. And we had to package this material. Can't easily recall the name of the company, but when we packaged this, all these key components, including the electrical components and the mechanical components, we had close to a zero failure rate. So maybe not during the operational phase, but getting it to where you need it is oftentimes a key part of this reliability piece.
Todd, any other comments to add there?
I think my colleagues did an excellent job answering that. For me, going back to heterogeneously integrated systems, we believe that that's our future. We feel pretty good about the mechanical interconnects, but again, managing those interfaces, the communication protocols, they are going to be transistor-based, right? So think about a SerDes block, for instance, that's sending data from one chiplet to another. Those are going to be subject to the effects of ionizing radiation, and knowing how to handle that is going to be a challenge.
So we're down with just a very small amount of time left, and a question came in from the audience that I suspect could power almost an entire additional panel. But just some real quick answers to how is the field of artificial intelligence and machine learning playing a key role in the domain of extreme environmental electronics? Rusty, you want to kick that one?
Yeah, I mean, this is a key component in the energy industry, right? Because we're trying to become digital, and I think we largely are, but not all the companies are in the same at the same speed. So we're trying to do as much processing as possible at the site and location, edge processing, and just retrieve what we need and transfer that back to, say, the home office, wherever that may be. It could be Houston, but it could be Midland, to be able to make decisions, to make better decisions around how to operate that field. The problem is, with this machine learning and artificial intelligence, even when you do that edge processing, people are getting so much data to canvas and look at that they're not looking at it. So part of the challenge, I think, is even with artificial intelligence and machine learning, what do you do with all this data, even when it's coned down to maybe a smaller subset? Yeah, you can program it to give you some things to kind of look out for, some highlights, but I think it's a bit of a problem that when you're collecting and sensing all this data, it overwhelms the humans.
I think that's going to be a good place to end since we've run out of time. Great. I'd like to thank the audience for your attention and your questions, and I'd like to thank my panelists for their insights into this area. So thank you, and we look forward to engaging more with you during the breaks.